for coming to this afternoon session. I'm very pleased to introduce Belinda Tzen, who is going to be speaking on a MeanField theory of lazy training in two-layer neural nets. Thank you very much.
Hi everyone, so this is joint work with my advisor, Max Roginski, and we are from the cornfields of Central Illinois. So just a note, all of the work I'm going to describe here is going to be in continuous time. It can be ported to discrete time pretty straightforwardly, but that's sort of not where the novelty lies, so we'll leave that aside for now. What's of interest here is for a specific class of problems given in the title. We're interested in comparing the Langevin diffusion's convergence to the Gibbs, which we know happens in general, to what's in some sense the most efficient way of attaining the Gibbs in finite time. And we'll make that clear later, but most efficient will be in a strict control theoretic sense. So to get started, let me just set up the problem. We're interested in having set of data, inputs X, labels Y, labels in the reals, and some sort of predictor that is a sum of a nonlinear function of the data and weights over some very large set of weights. And we're interested in evaluating this predictor relative to the squared loss and considering what happens as the number of neurons goes to infinity. So the mean field limit where they're all exchangeable. And probably most of you are familiar with this problem by now. It's like several years old, but I should probably motivate it because for most of you who haven't been living under a rock, you've probably heard that, and you probably know very well that neural networks benefit from very great depth rather than width. For example, Facebook and Google are using very deep rather than very wide networks to classify all of the things. And in fact, we have some essential benefits of depth results that are all lower bounds with respect to the width you need to trade off for depth. So they're all of roughly the form. There exists some function that's efficiently approximable by neural networks of some depth that is not small. But if you want to approximate the same function with a shallow network to the same accuracy, you'll have to incur a cost in width that's exponential in dimension. So there are lots of results in this vein, and essentially they all deal with uniformly-ish oscillatory functions where depth helps you a lot, but which will be penalized greatly when you try to reduce depth and approximate the same thing with something very wide. Now we care because to back up like to the 80s and 90s, we were interested in neural networks because of the so-called universal approximation property, which says that even shallow networks with a single hidden layer can approximate basically any interesting function to arbitrary accuracy. And here, almost every interesting function would be continuous functions over a compact set. So it's really not restrictive. The only catch being that, well, you might actually have to pay for dimensionality here. But that's fine, I guess, if you want to take your neurons to infinity. And in fact, all the results along these lines do not care about recursive dimensionality. And on the other hand, there's also been, as I'm sure most of you have heard and are aware of and are involved in, work on so-called lazy training, which says that in many cases, when we have very wide shallow networks, training with SGD does not result in the weights moving very much, which is a so-called lazy training regime. Now, of course, there are some caveats here concerning the width of the network relative to number of data points, so-called overparameterization, which is very sensible and kind of necessary if you think about it. There's also relationships to step size. So if you go too aggressively, you will exit this regime. There are connections to margin and stopping and so forth. And of course, there's also the connection to the so-called NTK, the neural tangent kernel, which says that, well, if the weights don't move very much, then they're close to the linearization around initialization, which says that, well, then that's kind of disturbing because here we have this highly nonlinear function And we're saying that it's closely approximated by something linear. And luckily we have caveats that say, well, this happens only sometimes. So now that I've motivated this mean field limit, it's kind of immediate how we would transfer this whole thing to the space of measures. Instead of having an empirical distribution of the weights, we have instead a measure over the weights. And likewise, instead of considering the risk given by a very large collection of weights, we have the risk relative to a measure over the weights. And here notationally, this won't be super important, but just to make it clear, this R0 term is the model independent data term. The F tilde term is the cross terms with respect to the model and data. And this K term under the integral comprises the quadratic terms. So it looks a little weird, but we'll replace this notation in a little bit. And now that we've set up this sort of measure theoretic formulation, we can also think of the laziness of training as entropic regularization, where instead of considering minimizing just the risk of the weights or the measure, we consider minimizing the free energy functional comprising the risk at some terminal time and some divergence relative to some sort of prior on the weights, the prior reflecting initialization. And note that this is sort of not a new idea. For example, May et al. Did this back in 2018, where they're regularizing with respect to Lebesgue measure, so relative to some sort of uniform prior over the weights. And here we're considering, as I'm sure you all know, initialization is often Gaussian, regularizing with respect to a Gaussian. And because we're expecting that laziness of training is observed whenever we stop the algorithm, at least up to some time, finite time t, an upper bound, then we can say moreover that this whole pathwise, we can regularize instead the path measure over the weights relative to, instead of a Gaussian, the Wiener process from 0 to t. So regularizing the evolution of this path measure relative to a Brownian motion truncated at t. And here we have two parameters of interest. We have this familiar probably to most of you inverse temperature parameter, which will come into play when we discuss the Gibbs distribution. And of course, we have this optimization time t, which will also affect the strength of the regularization. So as you optimize for longer, this prior becomes more diffuse, variance grows, and so we're regularizing less as we go over time. Okay, so as I just sort of foreshadowed, free energy minimization is going to be a matter of balancing two different considerations. So of course, we're going to care as before about the risk at the terminal time t necessarily, but also we're going to care about the pathwise behavior of this measure relative to the Wiener process over the same time interval. So trading off risk minimization and entropic regularization. And so you might ask, okay, didn't I just make things really complicated by making this pathwise rather than just considering the terminal risk and the terminal divergence? And maybe yes, but optimality says no, because in fact, we can decompose the divergence term using the chain rule for KL, which will give us, well, if we choose correctly, the divergence at the terminal time, and then the divergence over the interval from 0 up to t, open endpoint at t, conditioned on what happens, the realization at time t. So if you look at this thing, then especially the first term, you'll notice that the integrand, okay, it's this nasty conditional pathwise thing, but it's actually independent of the terminal density that you achieve. So by optimality, remember KL is not negative, then whatever this terminal density is, mu t almost surely, that thing has to be a Brownian bridge so that it corresponds to the Wiener measure pinned at whatever it's pinned at time t. So then in fact, the entire integral goes away and we're left with a static problem. We're optimizing without loss of generality over the class of Brownian bridges that don't have that nasty pathwise term. So free energy minimization over path measure becomes one of the risk at the terminal time and the divergence at the terminal time. So we didn't actually end up with a much hairier problem. Moreover, because this free energy is strongly convex in the terminal density, there exists a unique optimal measure, and it's characterized by this so-called Boltzmann fixed point condition that looks like this. So it comprises a potential with inverse temperature beta and a Gaussian that reflects the strength of regularization or optimization time. And if you're looking at this Boltzmann fixed point condition being like, okay, where did this come from? I would just ask you to consider, for a quick and dirty way of getting at this, no regularity conditions, whatever, to just, because this free energy functional is strictly convex, just take the functional derivative, set it to 0, and solve for ut, and there you go. Of course, it's a lot more delicate than that, but just so that this thing doesn't look very mysterious. Okay, so some of you may have looked at this pathwise divergence minimization and been like, okay, it looks kind of familiar, like some classic problem. And for those who know this classic problem, well, it's the Schrodinger bridge problem, which asks for some diffusion process that puts some drift on top of standard Brownian motion run over some time 0 to t, finite t. What is the way of achieving some desired terminal distribution such that we minimize the total work done from 0 to t? So total work done here being the Euclidean norm squared of your control or drift over this interval. And this is an Occam's razor consideration, which is morally sort of what we want if we don't get to observe this process at various times in between. It's a prior towards a very sort of gradual evolution of this process, rather than saying, okay, well, we're not looking at it, but we assume that there can be some like strong force that randomly comes in and strongly perturbs it at random intervals. And Gersano's theorem will tell us that, well, lo and behold, this expected total work done is nothing other than the pathwise KL between the uncontrolled and the controlled process. So hopefully things are looking like they're coming together a little bit. And where are we going with this? Well, from there, it's kind of immediate that we would be able to set up an optimal control problem, which says that, okay, for a diffusion process, which is your standard Brownian motion with some drift attached to it, what is the drift or control such that the law of the process minimizes this free energy functional, the one we described before? And note that this has a very different flavor from asking about the mixing time of the longevity diffusion process. So it's not saying how fast can this thing get to the Gibbs distribution. It's actually saying, well, we want to get to the Gibbs exactly by some finite time. And of course, that's a lot more ambitious, and that, I mean, if you think about it, that should cost us in various ways. Okay, so to fully make this a control problem, again, we say that, okay, we have a diffusion process, which is a drifter control on top of a Wiener process. We're not touching the Wiener process itself. And we want to minimize the expected cost comprising this running cost, control cost, and a terminal cost, where here the terminal cost is the risk attained by the terminal measure. So, I mean, it looks like your standard control problem setup, you'll get a value function out of this somewhere, right? But okay, like life is actually bad here, because now this, like by optimality, this process is going to incur the dependence on this terminal condition, terminal cost, this risk at the terminal time. And this dependence is going to propagate in ways that we're generally not going to know how to deal with. It's an instance of McKean-Vlasov dynamics, which are generally not analytically tractable because they have an evolution of the optimal density governed by this coupled set of forward-backward equations. So we have naturally the Fokker-Planck equation forward. Here we're starting from 0, Dirac delta 0. And we have the HJB equation governing the evolution of the value function going backwards. And with a terminal condition that is given by what we would say is the cost, the risk contribution of this, the weight given by the space variable. And if the HGB equation doesn't look as friendly to you as the Fokker-Planck, which I assume you're all very friendly with, then I would ask that you consider the Bellman equation in discrete time, the necessary dynamic programming iterate for optimality, and then take the limit of the time step to 0 and convince yourself that it should look something like this. Gradients will have to appear because of optimality. Okay, so we have this HGB equation, and okay, what do we do with it? Well, it corresponds to the Cauchy problem and has this sort of terminal condition. And what do we do with it? Well, luckily in our case, we can perform a log transform on it and get back another Cauchy problem, one that is a lot nicer looking. And here, the terminal condition, we've gotten rid of any dependencies on things that are independent of the space variable. And lo and behold, Feynman-Katz gives us the solution to this new Cauchy problem, and then we invert the transform and we get back what should be our value function. And if you look at this and you're somewhat familiar with control, you'll say that, well, yes, it looks something like what it should look like. It's an expectation over what you want at the terminal time given where you are, space variable wise, at the given time t. Okay, so what does the optimal control look like? Well, like we said, the optimal control should be something like a negative grad of the value function, because, well, when the control cost is your Euclidean norm of the control squared, then, well, you don't want to be wasting any control effort going in directions that are not minimizing your value function. But by optimality, this sort of has to be the case. And that's not a useful characterization, of course, unless we actually know the value function. And here it's a matter of, okay, now we have this candidate value function, and let's ensure that it satisfies all our necessary conditions. So if we plug in negative grad of the value function as our control, then we actually get that the marginal satisfies via the Fokker-Planck equation, nothing other than our Boltzmann fixed point condition, which tells us that the terminal density is in fact that satisfying the Boltzmann fixed point condition, and therefore the whole thing solves the HGB equation, and we are done. And earlier I promised you that optimality would have to be characterized by a Brownian bridge. So if we plug this in carefully, then what we get in fact is that the optimal control looks something like this. Log grad of this quantity, and it's known as the Fulmer drift. So here we see that when Fulmer drift has been characterized as getting more desperate when you're far away as time approaches your terminal time. So sort of a deadline consideration, like the further away, the more desperate you are as you get closer to your deadline. Now, if you stare at this a little bit more and you're familiar with the SD corresponding to a Brownian bridge, you will say that, hey, this looks somewhat familiar. And in fact, our function f here corresponding to potential above is actually just the density of our optimal measure relative to the terminal Gaussian. And so, in fact, it is just the Brownian bridge where the terminal condition is marginalized over all possible realizations relative to mu star t. Okay, so I told you that you can get this value function, and at the end of the day, you have this Fulmer drift that is an optimal control. And so life is good, but it's not actually good because, well, you should have some exceptions, which are that first. Well, optimal control requires knowing your desired terminal distribution. Here characterized by the Boltzmann fixed point condition, which is all great if what we want is to be able to sample efficiently from this terminal distribution, but here we're actually trying to arrive at it. So there's some manner of like putting the cart before the horse. And secondly, there's the fact that, well, lazy training happens. So isn't this optimal control approach somewhat overkill in the sense that, well, some greedy approach such as SGD or in continuous time enlargement diffusion should be able to do nearly as well. All right, why do you need optimal control if some greedy algorithm that will just give you something that's nicely entropically regularized anyway? And to that end, we might want to compare following three processes. We have the process given by the optimal control or Fulmer drift, this Brownian bridge type thing, which has a nasty expectation that you probably don't want to implement, you probably don't know how to implement, versus the overdamped Langevin using the optimal law, which is seemingly more tractable, but we still have this optimal law to deal with, and then versus Langevin with not the optimal law, but the law at any given time t, which should be implementable and like the most sane counterpart you would want. So here we have, as before, our two degrees of freedom. We have beta, the inverse temperature parameter, and T, our optimization time. So inverse temperature plays the role it plays in most of these considerations. So it's going to affect the Gibbs distribution in the sense of the sharpness around the modes. Whereas the time is going to govern the strength of this regularization with respect to the Gaussian. So the longer you optimize, the weaker this regularization. And so there will be various trade-offs between beta and T, and the question is, well, how exactly do they interact, and in what cases and what regimes might the Langevin with various choices of beta and T be comparable to the optimal Fulmer drift, or will it never be? Okay, so what cases are we interested in? Well, first of all, there's the Boltzmann fixed point condition again, and we can reason about the potential in various ways. If it's strongly convex, we expect that life will be good, right? If it's non-convex, well, life will be not so good, but we can also consider when it's almost convex or semi-convex. So convex if you add some smallish quadratic term to it, or when it's hopelessly non-convex, where no matter what you do, it's very, very far off from being convex. So we're going to get at these considerations via what are known as log-Sobolev inequalities, which tell us about the convergence in Wasserstein 2 distance to the Gibbs distribution of a Langevin diffusion. So if something satisfies a log-Sobolev inequality with constant c, then it will converge exponentially fast in the reciprocal of c over time. So small log-Sobolev inequality is constant, is good, and large is going to make life very difficult. So in our strongly convex case, we can't really make any statements about the potential in general, but the quadratic regularizer will dominate. And so all in all, this regularized potential will be strongly convex and life will be good. Here we have a strong convexity parameter of 1 over t minus beta kappa, where kappa is, of course, what could be the maximum concavity of this potential, so to speak. Then we have in the convex case, the log-Sobolev constant as follows. So if we choose beta times t to be the factor of 1 over kappa, then our log-Sobolev constant will be something that's O of t, and life will be generally pretty good. We'll converge exponentially fast to the Gibbs distribution, and sorry, I just had a spam call. We'll converge exponentially fast to the Gibbs distribution, and if we want accuracy epsilon, we'll incur this additional cost of log 1 over epsilon, which can be sort of viewed as the price you pay for algorithmically for step size in terms of the smoothness as you approach optimality. So recall that Fulmer knows where it wants to go and it knows when it wants to get there by, so it can adjust its step size accordingly. But here, you're paying this 1 over epsilon term because, well, you don't know, you're just being greedy. And as you get closer to convergence, then you're dealing with flatter and flatter regions and you're not being as efficient. And here it's best to choose time t being 1 over, of epsilon, and we're good to go. We get convergence pretty fast. And sort of on the other hand, if this potential, even with the quadratic regularizer, is not convex, then life will be hard. The log Sobolev inequality will incur a cost that's will be of size exponential in dimension. And what does that mean? Well, that just means that here the choices of beta and t do not correspond to lazy training, in the sense that Fulmer will get you to the optimum exactly by time t, but just to get epsilon close, so we're not even talking exactly, just epsilon close, Langevin will require an additional factor of exponential in dimension amount of time to get there. And that's kind of what we would expect if this quadratic regularization corresponding to this entropic regularization with respect to the Gaussian is pretty weak. Okay, so now we're left with considering, okay, there's this qualitative gap between the convex case and the non-convex case. So in the convex case, we have log Sobolev inequality that looks like this thing on the right, sorry, on the left, and in the non-convex case, we get this exponential dimension cost. So sort of philosophically, that's what you want, in the sense that, well, things that are convex are qualitatively very different from things that are non-convex. On the other hand, we're not making this a problem about convex or concave and log concave densities because it's not very interesting, but also because, well, if we're going with the metaphor of lazy training, laziness is sort of this behavior, and as such, it's sort of more on a continuum rather than something that's dichotomous. So we don't want to say is something lazy or is it not lazy, you know, just like how lazy, and can we get at that? So if we look more closely at the log Sobolev constant for the non-convex case, we'll see why it has this exponential dependence on dimension, which is that this xd term comes from the maximum fluctuation of this, what we call G here, this potential, over some compact set that could be of size sort of root t. So if you think about it, well, this is actually pretty bad in the sense that a strongly convex function will have a pretty bad log Sobolev constant using this bound, but obviously it will have a very good one using the correct one, which accounts for convexity. So what can we do about this? Well, we can decompose this semi-convex potential into a convex portion and sort of this non-convex slot portion, which we'll assume is bounded in magnitude. And from here, we can say, okay, well, we can use a perturbation argument to say that, yes, we'll have this xd term, but it's actually not going to be very large. There'll be some small constant in front of it that'll make things tractable. Or we can say that, well, because we're interested in dynamics specifically, we'll just use Girsanov and say that we can reason about the convergence of the convex portion, which is exponentially fast, and then the divergence incurred by this non-convex slop portion, which will be bounded and not so huge over some not very long time t, And it'll be on the order of this non-convex magnitude m squared t. And if m is not large by assumption, then again, we can choose t to be O of epsilon, hiding some number of Lipschitz constants, and we're good to go. Okay, so the last part would be comparing Langevin with the optimal law versus the at time t law, which is what we could actually hope to implement. So when we look at these two processes, well, we can say that the strong solutions, any two strong solutions will evolve with the difference in norm. It looks like this. So nothing fancy here. This is an equality. And the thing to note here is that we have this -1 over t term, and then this beta term, which will account for some difference between the law at time t and the optimal law at any given time. And here the difficulty is that, well, no matter how you slice it, that difference between mu t and mu star is going to be difficult to deal with, and it's going to affect basically any two strong solutions. So even in optimal coupling, we'll have to wrangle with this difference somehow. And also, morally, we can reason about, we could probably say that we can reason about the Lipschitz constants of the optimal potential with mu star, because it should be nice in various ways. But just say that we have nice Lipschitz constants for mu t for any mu t and initialization is sort of an iffy proposition. Like, we don't really want to do that. And in fact, what can be said in the general MKV case is that if this MKV term here, beta or negative beta, is not small enough, then in fact, there will be multiple stationary distributions and life will be very hard, and it will be just very difficult to talk about conversions. So morally, what we need here is to say that, well, 1 over t is a lot greater than beta, so that this process is sufficiently Ornstein-Uhlenbeck-like, and the MKV term is not going to pose too many problems, and we're left with something that's bounded and highly regularized. Okay, that's all I have. I guess there's like 5 minutes left for questions, so if anyone has any questions, go for it, I guess.
Thank you very much. Let's thank Belinda for that wonderful talk. And are there any questions? Yeah.
Sure. So this is just a very general question. What would be an example of a distribution that you would want to sample from, or this would be the best method that you could choose? You know, like, what is somehow, obviously there are other methods that work great for log concave distributions, but this has, you know, significant tolerance to non-convexity. What's the sampling problem that you have in your mind when you're thinking about this type of method?
Sampling or optimization. Because here, the Fulmer drift is very useful for sampling. In fact, it's, by definition, it's the most efficient way to sample from some desired distribution at some finite time t, if you know that distribution. And it's most efficient in this work done L2 norm squared sense. But here in this optimization problem, we're saying that, okay, we're going to achieve some optimal distribution at time t. Here, the Boltzmann fixed point condition satisfying that minimizes our free energy functional, but it's not actually going to be useful in the sense that, well, we can't get there ahead of time because we don't know mu star satisfying Boltzmann fixed point condition. So here the problem is more comparing the Langevin algorithm with appropriate law to Fulmer and saying that, well, hey, lazy training happens, which means that we can achieve optimality pretty efficiently. So how close is, or how efficient is efficient. Does that answer your question at all?
Okay, great. Any other questions? Lan, okay, may have answered Lan's question as well. No? All right, okay, then let's thank Belinda again. Thank you.
Thank you all for participating.
Okay, and so we'll begin again and maybe at 10 till